way type deduction, which is Decltype type deduction. This is introduced with C++11. If I say Decltype of some name, then this will give me the actual declared type of the name. So in this case here, if I have x as an int and rx is a reference to a constant int, Decltype of x is just int. Decltype of rx is exactly what its declared type is. So Decltype of rx is reference to constant int. Decltype doesn't throw away references, doesn't throw away const, doesn't throw away all. There is a special rule in Decltype. If you say Decltype and then you give it some L value expression, some expression which is an L value, then Decltype will give you an L value reference as the resulting type. Now, this is not usually an issue in practice. It turns out most expressions that are L values already have a reference associated with them. As an example, here is a function called findVec. FindVec returns a reference to a constant vector of widget. By definition, all L value references are L values. If you have an L value reference, by definition, it is an L value. But there is an interesting side effect of this rule. Every name is an L value. But I told you that if I do Decltype of a name, it gives you its declared type. But now I just told you if I do Decltype of an L value, it always comes back with an L value reference. Well, names are L values. But it turns out that the Decltype name rule is more important than the Decltype expression rule. So, if I have this integer x, and I say Decltype of x, well, x is a name, so the type is just int. However, if I say Decltype of paren x paren, now, paren x paren is not a name. Paren x paren is an expression. X is a name. Paren x paren is an expression. Decltype of paren x paren is int ref. Decltype of x is int. Decltype of paren x paren is int ref. Because this is a name, this is an expression, it's not a name. For purposes right now, we can say, okay, this is interesting, but it doesn't make much difference to our lives. It will make a difference to our lives shortly. So that's Decltype type deduction. It turns out that there's many more subtle rules for Decltype type deduction. For most programmers, all they need to know are the two rules I've given you, the one about names and the one about L value expressions. That's it. But we're talking about type deduction in general, so the next thing I want to talk about is function return type deduction. In C++11, there wasn't a lot of it. Single statement lambdas, you could do type deduction on them, but you couldn't do type deduction anyplace else. In C++11, all lambdas are eligible for type deduction, and all functions are eligible for type deduction. So in C++14, it's extensive, which means that understanding the type deduction rules is more important than they ever were. There are two return type deduction specifiers. I can have a function which has an auto return type. If I have a function with an auto return type, it uses template type deduction. Now remember, template type deduction differs from auto type deduction in only one way, and that has to do with braced initializers. Remember, auto deduces a type for a braced initializer, even though a braced initializer has no type. So, if I have an auto return type, it uses the template type deduction rules, which means if you try to return a braced initializer, the code will not compile. The other specifier for a return type is Decltype auto. Now, Decltype auto seems contradictory. Decltype has one set of type deduction rules. Auto has a different set of type deduction rules. So what does Decltype auto mean? Decltype auto means do deduce the return type, and Decltype means use the Decltype type deduction rules. Let us suppose I have a function called lookup value. So lookup value, I pass in some context information so I'll know what value to look up. I have a static vector of int inside the function, and I initialize it to hold some value. So inside my function, I now have a static vector. What I want to do is look up one of the values in that vector. So what I do is I figure out the index into the vector by looking at the context information. So somebody passes me some information here. That lets me figure out which value in that vector is the one that I want. And now I return values sub idx. Now, this is a function for looking up a value. I want to return a copy of the value. Under those conditions, I want an auto return type. And the reason I want auto is because auto will make a copy. Notice this isn't auto ref. This isn't auto star. This is a brand new value. That's what auto gives me. It's important to me that if somebody says, look up value my context info, so if somebody calls this function, it's important to me that if they try to modify the result by, let's say, assigning 0 to it, I don't want them to modify my internal array. So it's important to me that this function return a copy of the value, not a reference to it. By using an auto return type, this returns just an int. Now, on the other hand, sometimes you actually want a reference to be returned. Here's a function authorize and index. It takes a vector of int and it takes some index. And it authorizes the user and then returns v sub idx. This function here is doing the same thing as an indexing operation on a vector, except it's performing access control. Which means whatever the vector indexing operation returns is what this function should return. This is going to return whatever v sub idx returns. The array bracket operator on a vector returns a reference to the referenced element. The array bracket operator returns a reference. I want to return that same reference. So in this case, I can say Decltype auto. That allows me to say things like authorize an index, myvec10 gets 0. Now, in this case, I do want this to compile. I want this function, authorize an index, I want it to return exactly what this thing returns. If this returns a reference, I want it to return a reference. Auto will be incorrect here. Auto would give me a copy. So sometimes you want an auto return type, but sometimes you want a Decltype auto return type. That's why we have both. So here's lookup val, lookup value. We saw this before. Let's suppose that lookup value, what I decide to do now is I decide to use a Decltype auto return type. Now, in the previous implementation, I used an auto return type because I wanted a copy. But notice I have a slightly different implementation now. What I've said is auto return value is value sub IDX. This is auto, so this is a brand new independent variable. And now if I say return val, well, using Decltype of auto here is okay because this is going to, the type of this is, if value sub IDX is an int, this is an int, which means I'm returning an int. So this will work fine. However, there are some people who have the habit of always putting parentheses around their return types, just as a habit. So if you were to change this implementation to say return paren, return value close paren, this is no longer the name of a variable, this is now an expression. Which means this is now returning a reference to an int. The return type here is int because retval is a name. In this case here, retval is an expression, paren, retval, paren is an expression. This therefore returns an int ref, which means what you're doing here is you are returning a reference to a local variable. These parentheses change the meaning of this return type. Now, most compilers will give you a warning that you are returning a reference to a local variable. But there's no guarantee you'll get a warning. Some compilers may not do that. Which means that if you have a Decltype auto return type, you need to be particularly careful about how you write the function body. Personally, I believe that deduced return types should be used carefully, and most of the time you're probably not going to want to use them. I think you're better off in most cases actually declaring the return type. However, there are some situations where it's just easier and it's no less clear to use a declared return type. We'll see some examples of that. Yeah?
Can it have const auto reference as a return type?
So the question is, can I have const auto ref as a return type? And the answer is yes. So if I go back one slide, two slides, I can make this const auto ref. I could make this just auto ref if I wanted to. So yes, you can adorn auto with references and consts if you want to, or pointers for that matter. In this particular case, I know that I have a vector of int, so I know exactly what type I'm returning. Occasionally you have a type where you don't know what it is because you're inside a template, in which case you don't know whether you want to return a reference or a value. And that will become clearer when we talk about proxy objects. So Decltype auto is a way to say, whatever is being returned here, I don't know what it is, but whatever that is, that's what I want to return. All right? So that's Decltype auto. So as rules of thumb, you should use auto if a reference type would never be correct. Auto will always make a copy, although you can't say const auto ref as you mentioned. And you should use Decltype auto only if a reference type could be correct. It's sometimes referred to as perfect returning. So Decltype auto is a way to say, whatever I get back from a function call, I want to propagate to my call. Yeah?
What is correct, or rather, what is incorrect reference type?
I'm sorry?
What is incorrect reference type? What do you mean by correct here?
So, as an example, if we go to, with this function here, lookup value, as the designer of this function, I do not want to return a reference to my internal vector. I want this to always be a by value return. As the designer of the function.
By correct, you mean it's not touching what it's not supposed to touch?
By correct, I mean that as the person designing the interface, I have made the decision that I don't want to return a reference, I want to return a value.
Okay.
So correct is determined by the person designing the interface. All right? So the guideline is to understand type deduction. Any questions about type deduction before we move on to more interesting topics? Yeah.
Reading at a style when to use auto and when not. Some would argue if you look at tailor definition and everybody is using auto, then we have to have strictly document, otherwise nobody can see from code which type is to be used or not.
So the question essentially is, are there some guidelines about when to use auto and when not to use auto? In fact, I think it might be the next guide. Okay. Very shortly, I'm going to be advocating that when you declare an object, you should prefer to use auto. And I'll be talking about the technical reasons why I believe that's usually a good idea. And at that time, we'll also talk about the resulting readability of the source code and things like that. So for purposes of declaring objects, I believe auto is usually what you should use. I'm not going to say 100% of the people in the world agree with that, but there's, I think, an increasing consensus that it's generally a good idea. But let's defer that discussion until we get to that time. Any questions about type deduction before we move on to other topics? All right, what I'm trying to do this morning is lay the groundwork for broader discussions later on. So we've talked about L values and R values. We've talked about type deduction. Now what I want to do is I want to talk about standard move and standard forward. And this is going to be the last piece of sort of general background information before we move on to more specific things. So the thing about standard move and standard forward is, first, you need to understand what they don't do. Move doesn't move. Forward doesn't forward. In fact, neither one of them does anything at all at runtime. They generate zero code. They are no ops at runtime. Which tells us what they don't do. They're both casts. Move is a cast. Forward is a cast. In particular, move unconditionally casts something to become an R value. Forward conditionally casts something to be an R value. So they're nothing but casts to R values. That's all they are. That's why they generate no code. They just tell the compiler, this is now an R value. So this is an essentially conforming implementation of move. The details won't make a lot of sense until we talk about reference collapsing, but this is what I want you to notice. Here's the name of the function move. It takes some parameter, which it returns after casting it. Even if none of the other code on the slide makes sense, it's very clear this function is nothing but a cast. That's all it does. You can think of move as R value cast. And there have been proposals to call it R value cast. Move does not move anything. Move doesn't do anything at runtime. There are no executable instructions inside that function. Now, I told you a few minutes ago that I'm not wild about deduced return types, and that I think in most cases it makes sense to write out the return type yourself. But I said in some cases there are exceptions. Look at the return type of this function. Type name, remove reference of t::, type ref. Inside the function, I have a type def called return type of type name, remove reference of t::, type ref. It's exactly the same text. Casting to. Which means that I have to type that here, have to type exactly the same thing here. That to me is not great software engineering. Which means that in C++ 14, I believe this is a reasonable place to use Decltype auto, because whatever you're casting to, that is the return type. So this is valid in C++ 14. The previous one is valid in C++ 11 or C++ 14, because deduced return types don't exist for regular functions in C++ 11. Turns out that C++ 14 also makes it a little bit easier to express the type you want to cast to. But for our purposes here, this I think is a reasonable use of a deduced return type. However, notice that we're talking about a function called standard move, and that's already in your standard library. So you don't need to write this function. Nevertheless, I think it demonstrates that occasionally it can be clearer to write code where you have a deduced return type. And in this case, I think saying this is going to return whatever the result of this expression is clearer than typing the same code twice. I want to talk a little bit more about move. Let's suppose I have a class for representing annotations. So when I want to create an annotation, I pass in a text string, which becomes the annotation. So here's a constructor for annotation. It takes a standard string. This is the text of the annotation. Now, this string that's passed into this function, I'm not going to modify. So I'm going to declare a const, because it's an in parameter, not supposed to be modified. I have also passed it by value. Personally, I'm not wild about passing strings by value, but there is a body of information that encourages people in some cases to pass by value. There was a relatively well-known blog post a couple of years ago called Want Speed, Pass by Value. There have been some conference presentations which say pass sync arguments by value. So let us assume, for whatever reason, we have decided we're going to follow this advice, and we're going to pass things by value. So what we decide to do in this particular case is pass the text of the annotation by value, which maybe is efficient, maybe is not efficient. That's not our concern here. And it's const because we don't plan to modify it. It's an input parameter. So inside the annotation class, we have a string data member. And here is the constructor. And what we're going to say is, okay, I want to take this text and I want to move it into the data member. Yes?
Why do you have to implicitly pass type forward? Why doesn't it deduct the type?
I'm sorry?
Why do you have to implicitly pass the type forward?
All right. So the question is, if we go to the forward implementation, the question is, so when you call forward, you pass in the type t.
Yeah.
So the question is, normally with function templates, we deduce the type. The problem we have here is, let us assume, let's just get rid of that parameter t and see what things would look like. Let's assume that this t were missing. Under those conditions, I would just say it's forward of parameter. The problem is, this is an L value. This will always be an L value. Which means that forward would go, oh, it's an L value, and it would keep it as an L value. The situation we have here is that we need forward to do something not based on its parameter, but based on how this parameter was initialized. We're actually reaching back to function calls. And interestingly, it turns out if you take a look at, since you've actually looked at forward, if you take a look at the forward implementation, they go to some trouble to make sure you can't forget to pass this. It turns out if you try to call forward a param, it won't even compile.
Yes.
And the reason it won't compile is because they understand forward, just passing in a parameter, will always give you the wrong answer. So they actually have designed the interface to forward, and I'm not showing it in these slides, but they've designed the interface so you cannot forget this parameter. And the reason is because this type T, that is what has the information as to what was passed at the call site. Does that help?
Yeah.
Okay.
One more question about that method. So basically, if we call login process, we expect an L value to be copied and an R value to be moved in that method.
Okay.
But the param is non-const, so the function signature doesn't give me any guarantees that my parameter isn't going to be modified anyway, whether it's an R value or an L value.
Okay.
Isn't that a bit of a drawback?
All right, so the observation is that when I pass in this parameter here, it doesn't say const, it doesn't say non-const. All it says is, I'm taking anything that you wish to pass. This universal reference typically is used for forwarding to other functions. So the way that you read this is you say, I will take anything you pass me, const or non-const, volatile or non-volatile, L value or R value. I will take whatever you give me, and I'm just going to pass it to somebody else. This is a pass-through parameter. And that's what's actually going on here. What we're doing here is, whatever's passed in here, we pass it unchanged to one of these two overloads here. However, having said that, if I'm the author of login process, if I know that this will never be modified, for example, if I know that these processing functions will never modify, if I know that, then I should declare this as a reference to const. But in this case, notice that process itself is overloaded. And presumably, because this is taking an R value reference, this pretty much says, I want to modify this parameter. So I can't make any guarantees here, because the problem is, if somebody passes me an L value, maybe it'll be copied, but if somebody passes me an R value, maybe it'll be moved. So I can't put the word const there because I just don't know. All right? Yeah.
Well, what if we want, before a process has two overloads, one is const reference, the other is permanent.
Yes.
So in one case, we don't touch the thing at all. In the other case, we take control.
Correct.
Can we preserve this?
All right, so the question is, in this case here, I have a function. I'll make it a little bit more conventional here. We have a reference to const to the first overload. This is conventional. This is a copying function. This is a moving function. And so the question is there some way that we can preserve the appropriate information? That's what a universal reference does. Universal reference basically says, I will preserve all the characteristics of what are passed to me. I will remember if it's an L value or an R value. I will remember whether it's const or non-const. I will remember whether it's volatile or non-volatile. Remember that if somebody passes me, for example, something which is const, when we went through the rules for template type deduction, const would be deduced as part of T. So the const would be retained here. Does that make sense? If somebody passed me volatile, the same thing would happen here. The other thing that is preserved is if an L value is passed in, this type will be a reference. If an R value is passed in, the type will be a non-reference. And that information is used by forward in determining whether to perform the cast. But this is a conventional forwarding function. It accepts anything, preserving all of its characteristics, and it forwards those to overloaded functions which pick apart whether it's an L value or an R value. Does that answer your question? Okay, we will have much more time to talk about L values and R values and all that other stuff, but I want to get to a couple of more concrete guidelines which you can use on a daily basis, and in particular, I want to start with why you should prefer auto, because this is a question that came up earlier. I could say widget W, I could say auto W, assuming that I have some initializing expression. The question is, why am I advocating auto? Because I am advocating auto most of the time. Let's start with the least important thing first. The least important thing is mandatory initialization. If I say int x, or rather int sum, it might or might not be initialized. It depends on exactly where you type it. Which means it could have a garbage value. If I try to say auto sum, that won't compile. I have to give it an initializer. It's not a big advantage, but it's a little advantage. So let's go to something that most people run across more quickly. It actually makes your code easier to read in some cases. If I have a vector of string iterators, and I want to do something for every one of those iterators, I could say for standard string iterator SI and VSI, I have to type all this, or I can just say for auto SI and VSI. And this means for whatever is in this container, do it for each one of them. This is not only less to type, I believe it's clearer. Furthermore, if you change this later, maybe to be a const iterator, you have to change this too. Whereas with auto, it automatically updates. If I have an algorithm, it takes a begin iterator and an end iterator. Let us suppose that inside my algorithm, I need to make a copy of the first element of the range. For purposes of this example, we'll assume there's at least one element in the range. So the question is, if I have an iterator, what is the type of thing the iterator points to? All I have is an iterator. I need to know what is the type that it points to. Everybody knows it's iterator traits of iterator, colon, value type. I'm sure you use that daily. Except that iterator traits of iterator is a dependent type, which means you have to precede it with type name. So you could say type name, iterator traits of iterator, colon, value type, or auto. I do not believe there is anything ambiguous about what is happening in this statement here. This, in addition to being harder to read and harder to maintain, this makes it more complicated to understand what is actually going on. So that's a more important advantage. But so far we're talking about pretty minor things. There are problems with what I call type shortcuts. A type shortcut is where you use a type that is almost the right type, but not quite. If I have a vector of int v, and I want to know how many elements are in the vector, I could say, okay, SZ is an unsigned, that's how many elements are in the vector. The problem is, the size function for a vector doesn't return an unsigned. If I have a vector of t, the return type of size is, as everybody knows, vector of t, colon, size type. How many people write vector of int, colon, size type? How many people use that routinely? Nobody. One person, great. All right, good. You are a good person. Everybody else is not so good. The thing about this is that, for example, on 32-bit Windows, to choose a particular example, unsigned and vector of int, colon, size type are both 32 bits in size, which means you're good. It's the same type. But if you then go to 64-bit Windows, unsigned is 32 bits, and vector of int, colon, size type is 64 bits, which means you're trying to store a 64-bit value in 32 bits. Maybe you get a warning, maybe you don't. How many people, when they are writing unit tests, routinely test with more than 4 billion elements? Because this will only fail if you have more than 4 billion elements in your container. Yes?
Well, actually, you should use size t.
Yes, that's what we use.
You could use size t here. There is still no guarantee that size t is the same as size type. They are different types. There's no guarantee that they are, in fact, the same type. If you want to have a guarantee that you're using the right type, that's what you want to say. Or you're going to have to actually say exactly what it is. Size t is probably safer than unsigned, but it's still no guarantee that it's correct. I have a map of strings that map to integers. I want to do something for every element of the map. So I say, I'm going to create a reference to const of every pair in the map, because we know that the map consists of pairs. So what I want to do is, for every element of the map, I don't want to copy it. I just want to get a reference to it. So for every element of the map, I'm going to have a reference to a const pair from string to int. This code compiles, links, runs, probably passes all your unit tests. The problem is that a map from string to int does in fact hold pair objects, but the pair objects are of type pair const string int. The key is const, which means this is the wrong type. Pair of string and int is not the same as pair of const string int. So the compiler goes, okay, every pair in here is different from the pair over here. But because this is a reference to const is permitted to bind to temporaries. So the compiler proceeds as follows. It takes the first pair of the map, it creates a temporary pair, string and int, and in doing so it copies the string from the pair into the temporary pair, which means you just paid to copy that string, which is what you were trying to avoid by using the reference. It binds p to it, it does something with it, and at the end of the iteration, it destroys the temporary, which means it destroys the string that it copied, and it moves on to the next element of the map. So the first thing is, it's grotesquely inefficient. The second thing is, when you wrote this code, you probably assumed that the reference p actually referred to an object in the map. That's what you were hoping for, is it would actually refer to an object in the map. Which means if you did things like take its address, you would expect to get a pointer to something in the map. But that's not what's going to happen here. What you would do is if you took a pointer to any of these temporaries, you will get a pointer to a temporary object, and that pointer will dangle at the end of the loop iteration. So for example, if you put the pointer into another data structure, you now have a data structure with a dangling pointer. So this particular construct has the dual advantages of being slow and wrong. But it looks right. Because look, a map from string to int, a pair from string to int. If you don't remember the const, bad things occur. Or, if you just say auto, in which case you will in fact get exactly what you want. Generally speaking, my experience is that people start by looking at auto as a typing convenience. But the more you look into it, the more you realize that it actually can prevent certain kinds of mistakes in your programs that are easy to make by accidentally typing the wrong type. Any questions on this example? Let us suppose I have a lambda expression. So here's my lambda expression here. Now, if I want to store the result of a lambda expression, let's say in a local variable, if I don't use auto, I'm in a difficult situation because I don't know the type of the lambda expression. Every lambda has a new type. What I can do is I can store the result in a standard function object. How many people are familiar with standard function objects? All right. For those of you who are not familiar, you can see from the syntax standard function, it's a template. And the template takes what turns out to be a function signature. This says standard function is an object which can refer to anything that can be called like a function that takes an int and returns an int. A standard function object is a generalization of a function pointer. That's what a standard function object is. And it is the only practical way, if you don't use auto, to store the results of lambdas. So here's a lambda, it takes an integer and it returns this value here. I can store it as a standard function object. Standard function, clearly a template. This says f1a, this object here, can store anything that can be called with an int and it returns an int. Which could be a function pointer, but it could also be, for example, a lambda, as we've got here, or some other custom function type. The thing is, this class, standard function, I don't know what it looks like. But somebody wrote it has a certain number of data members, and what that means is it has a certain fixed size in memory. Every class has a fixed size in memory. So I don't know how big a standard function object is, but I know it's a fixed size in memory. In this particular case, I'm capturing A and I'm capturing B. I don't know what A and B are. I don't have enough context here to know what A and B are. Because we don't know how big A and B are, it is possible that the amount of memory needed to store A and B is more than the size of a function object. And if that's the case, it means you can't put the lambda into the memory for the function object. It won't fit. The code will still compile. What happens is the constructor for a standard function object will allocate memory on the heap. Which means this line here, the closure could be on the heap. The closure is the object resulting from the lambda. So this line here might dynamically allocate memory. On the other hand, if I have exactly the same lambda and I put the result into an auto, auto is exactly the type of this lambda expression, which means it's by definition, it will be large enough to hold all the data members. Which means this object f1b is definitely not on the heap. So auto is the most efficient way to store function objects in general, lambdas especially. So there's a number of reasons why auto is a good idea. It makes sure that you initialize things. It tends to lead to code that is shorter and in many cases clearer. It avoids unintended type conversions and type shortcut problems, and it's the most efficient way to store closures. There are some issues about any of the advantages we talked about, why using auto has technical advantages simply beyond being shorter to write.
This function, the lambda function, could you actually define a specific type instead of this auto for that particular lambda?
So the question is there any way for me, any way other than auto, for me to say the type? And the answer is no. Because this expression has a custom type. The type hasn't been invented until you've typed the expression. So there is no way that I know of, other than auto, to achieve the effect of this statement. The closest you can do is this. Now, what you can do, for example, for this, if I write this expression here, so I have to use auto, but if I use if I use auto here, if I wanted to make another copy of exactly the same closure object, so I want to have multiple copies of this lambda, then I could declare, let's say, F2C, and its type could be Decltype of F1B. So once I have one of them, I can use Decltype to find out what the type is. But the only way to get it the first time is to use auto. So these are reasons why I think auto has technical advantages, and it's why I encourage you to use it by default. Having said that, there's a couple of cases where auto doesn't do what you want. The first one has to do with braced initialization. We talked about this a little while ago. In C++ 11 and in C++ 14, if I say auto x1 brace 5 brace, this declares an initializer list. This is unique to brace initialization. If I say auto x2 gets 5, x2 is an int. If I say auto x3 with parentheses, x3 is an int. If I say auto x4 with braces, it's an initializer list. In C++ 11 and C++ 14, and I'm now talking about the standards as opposed to what particular compilers might have decided to do. If I say auto x equals and then I have some expression, the Decltype of x is not going to be the Decltype of the expression. Instead, the Decltype of x is going to be more or less an initializer list of the Decltype of the expression. Although I've already mentioned N3922, and you now understand that Microsoft's compiler already treats this the same as these two, and that is now in draft C++ 17. Nevertheless, for the foreseeable future, if you are using a compiler other than Microsoft's most recent community technology preview, or using cross-platform compilers, everything I've said here is true, which is that this will deduce an initializer list. In many cases, that's not what people want. The second thing you have to worry about are proxy types. A proxy type is a type that acts like some other type. And the most common example is vector of bool. Now, vector of bool is not a commonly used class, and in fact, at this point, it's kind of famous for this. The only reason I'm using vector of bool is because you can look this up in your header files and verify that everything I'm telling you is true. The more general concept of using proxy classes is much more widespread than vector of bool, so don't confuse the example with the broader picture. Vector of bool is the example, because that way you can look it up in your header files. But proxy classes are more common than that. So in this case here, if I say b1 is a boolean and it's vb sub 5, then b1 is bool. That's not a surprise. If I say vb sub 5, now conceptually, my vector of bool holds bools. I mean, that's what it says. It's a vector of bool. But vector of bool is required to store its booleans in a packed representation, 1 bit per bool. The problem is that the array bracket operator on a vector returns a reference to the element. You can't have a reference to a bit. The smallest addressable unit in C++ is the char. There's no such thing as a reference to a bit, which means this cannot return a reference to the bool. As a result, it returns something else. It returns what is known as a vector of bool : reference, which is a class type. Now, most of the time you're not going to be able to tell the difference, but occasionally you will. For example, if I were to assert that the address of B1 is not the same as the address of B2, well, they should certainly have different addresses. They're different local variables. But if I were to assert that they have different addresses, the code won't even compile. And the reason it won't compile is because I'm trying to compare a pointer to a bool and a pointer to a vector of bool : reference. That would be one way you could tell that you're not actually getting a vector of bool, or rather a bool like you thought you would. Now, I told you that a proxy type exists to act like some other type. And hidden proxies are often used only for temporaries. The idea behind a hidden proxy is it's hidden. You're not supposed to know it's there. Which means that its lifetime usually is assumed to be one statement. Proxies often hold pointers or references to other temporaries. In GCC 4.7, which is the last one I checked, vector bool : reference. Now remember, conceptually, it is a reference to a bit. The way it's actually implemented is usually it has a pointer to the machine word in which the bit occurs, and an index into that word so it knows which bit to reference. So here I have this function make bool vec. It returns a vector of bool. Let us suppose that what I want to do is I want to get the value of bit number 3. That's all I care about is bit number 3. The only reason I'm going to call make bool vec is to get the value of bit number 3. That's all I care about. So I can say bool b1 is make bool vec sub 3. That is a call to this function. It'll return a temporary vector of bool object. I will then index into the vector of bool object. I will get bit number 3, all stored into Boolean b1. We're good. There's no problem here. Code works fine. However, if I decide to use auto, because I have been encouraging you to use auto, if you use auto, what will happen here is make bool vec, that again creates a temporary object, temporary vector of bool. We then index into it to get number 3. Now remember, for vector of bool, the array indexing operator returns a vector of bool : reference. That's a temporary object. And remember, that temporary object in GCC 4.7 has a pointer to the machine word containing the bit. So, what happens on this statement here is, we create a temporary vector of bool, we index into it, we get back a proxy object which points to the machine word. We copy that into bit. So now bit has a pointer to the machine word. And then the temporary return type created by make bool vec is destroyed, which invalidates the machine word. So as of this statement, I hold a dangling pointer. So now, if I try to say, okay, the bit is the Boolean b2, the results of this are undefined. UB stands for undefined behavior.
Either wrong or right.
Pardon me?
It's either wrong or right value there.
It's either right or it's wrong. Well, it's actually undefined behavior. In particular, if you happen to be working, for example, on a multi-threaded system, other threads could have come in and used that memory between these two statements here. So you really have no idea what value you're going to get. And if you're on a machine that is checking memory accesses, or if you're running some kind of a tool that is checking for out-of-bounds memory references, then you're going to get into trouble right away. But the result is undefined.
And there is no compiler warning for this?
So the question is, if there's no compiler warning for this, I am not aware of any compiler that would issue a warning. And I mean, in this particular case, we know what's going on. But from a compiler's perspective, it would have to have a special rule for proxy types. Because from the compiler's point of view, all it does is create temporary, perform the indexing operation, which is just a function call, and put the result over here. I mean, it's not obvious that it's wrong.
No, each step is correct. Right.
Each step, from a compiler's perspective, each step in isolation is fine. So, I mean, we could imagine a compiler which knew about vector of bool, and therefore recognized that actually prolonging the lifetime of a vector of bool : reference was a bad idea. But I'd be surprised to see a warning. This is pretty much the category of don't do this. So again, the example that I'm giving you is vector of bool only because you can look it up in the header files. But I want to point out that it is very common in libraries based on expression templates. So I went to the Boost libraries just because Boost is a well-known repository of libraries. Boost.ugloss, Boost Expressive, Boost Proto, Boost Metastate Machine. All of these libraries use hidden proxy types. It is not an uncommon implementation technique in certain kinds of libraries. Which means if you use auto with these kinds of libraries, then you have a higher risk of compile and runtime surprises. I want to talk a little bit more about that because that doesn't really give you much useful information. But we have a very long stretch between the last break and lunch, which occurs at 1 o'clock. So we're going to take a 5-minute break now. It literally is 5 minutes. So it's enough time for you to stand up, maybe get some caffeine, and then come back. So we'll start again in 5 minutes.